Welcome to qnawire.
For part A, to show that the Bohr's model of the hydrogen atom, when the electron moves from the n state to the n-1 state, has a frequency that is given, we're going to use the fact that E sub n is equal to negative k squared e to the fourth times m sub e, where m sub e is the mass of the electron, e is the charge of the electron, k is the Coulomb constant, divided by 2 h bar squared n squared. We can use that in the fact that delta E is equal to E sub n minus E sub n minus 1, the two different energy states, and this is also equal to Planck's constant times the frequency of the emitted photon. We can use this to find the frequency of the emitted photon. So we have HF is equal to, we're also going to replace H bar with H over 2 pi. So we have negative K squared times 2 times e to the fourth. So the h bar squared gives us h over 4, but then you have that 2 to the left, so that gives us h squared over 2, so that 2 is what's up on the top there. That's where that 2 came from. Divided by Planck's constant squared. And then you have multiplied by 1 over n squared minus one over n minus 1 squared. So now dividing both sides by Planck's constant to solve for just F, and carrying through this negative sign, so that becomes a positive, this becomes a negative, this becomes a positive. And the fact that 1 over n minus 1 squared times n squared is equal to 2n minus 1 over n minus 1 squared. So that's just a little bit of algebra there. We find that F comes to equal exactly what we're expecting. We have 2, oh, we forgot our pi up top here. So this is supposed to be I squared, right? From Planck's constant, since it's h bar is equal to Planck's constant over 2 pi. So this is 2 times pi squared times the Coulomb constant squared, e to the fourth, mb, divided by Planck's constant, right? Because it was squared, but we divided by both sides by Planck's constant to get the frequency by itself, times n squared multiplied by 2n minus 1 divided by n minus 1 squared. We can box that in as version for part A. Part B wants us to use the Bohr's correspondence principle to show that as n goes to infinity, the expression varies as 1 over n cubed and reduces to the classical frequency one expects. And then he gives us this little suggestion to calculate the classic frequency and note that the frequency of revolution is mu over 2 pi r, where mu is v is the speed of the electron. Okay, so now we have, scroll down a little bit. We have the frequency f is equal to 2 pi squared k squared e to the fourth m sub e to minus 1 over n by Planck's constant cubed n cubed 1 minus 1 over n squared. Okay, so now as n goes to infinity and then as n goes to 0. So when n goes to infinity and then when n goes to 0, we have so first let's do n goes to infinity. You have the frequency 1 over n is going to be 0, right, for both of those. So the frequency becomes 2 pi squared k squared. So my cursor's wanting to cooperate there. E to the 4th b divided by bar cubed over n. So that means proportional to 1 over cubed. Which is what we were at. And then how about as it goes to 0? Well, as it goes to 0, that number is going to get larger and larger, but it's going to go away because we have the same thing on the top. So as n approaches infinity, the frequency reduces to the classical frequency. That's really all we needed to know, though. So we combine